Alrighty, welcome to lecture 26. So we're going to kind of finish up our discussion about liquids and solids. You can see really a lot of this has to do with intermolecular forces, right? So that's really, we're going to keep talking about intermolecular forces just a little bit first. And then besides talking about intermolecular forces, we're going to do a few examples where we try to, if once we understand the kind of intermolecular force that goes on between molecules, use that to predict some properties of molecules. And then finally, we're going to do a little calculating with this as far as when things turn from a solid to a liquid to a gas, how much energy does that take? So that'll be coming up in part B. All right, now before we get to any of that, oh gosh, we still got to really understand intermolecular forces. So let's do just a quick review of them. So we talked about last time, you got hydrogen bonding, you got dispersion forces, you got dipole-dipole. All right, first question I want to ask you. Do you remember which one of those three is the strongest? Which type of intermolecular force is the strongest? Dipole-dipole, hydrogen bonding, or dispersion? It's hydrogen bonding. Hydrogen bonding is the strongest kind of intermolecular force. All right, now just to, maybe we should review them a little bit, huh? So first off, yeah, they have different strengths. The weakest are called dispersion forces, or sometimes London forces. They're always weak. They occur in all molecules, but again, think of them mostly really for nonpolar things, because nonpolar things, that's all they got, okay? Dispersion forces are weak. They do get a little stronger as the molecule gets bigger. Another way of saying that is it has a higher molar mass, like its weight off the periodic table is bigger. All right, so if you're polar, you're going to have dispersion forces, but you're also going to have something even better to keep you and your neighbors connected. Polar molecules have a stronger force, 2, which are called dipole-dipole forces. And then the strongest kind of intermolecular force are called hydrogen bonding. They only occur when you look at the Lewis structure and you see FH, NH, or OH. If you see that as part of the molecule, that allows the molecule to form really strong attractions with its neighbor. Those are called hydrogen bonds. All right, so with that quick review, let's get into a few examples of trying to, guess what are the properties of some molecules based on the kind of intermolecular force that they make with their neighbor. All right, so I'm going to do a couple of examples of this. All right, let me flip over and we'll get to them. All right, so kind of the ultimate goal, once we understand these intermolecular properties, once we understand, you can have hydrogen bonding and dispersion forces and dipole-dipole forces, and they have different strengths, is we can use that fact to predict the properties of molecules. So if I give you two molecules, you can make a guess, a pretty good guess. Is this going to be something that melts at a high temperature or low temperature? Is this going to be something that has a high surface tension or a low surface tension? Is this going to be something that is viscous or non-viscous? All those properties we've been talking about, I guess in the last lecture really. So let's do a little example of that. So we're going to talk about two molecules, and my ultimate goal is going to be figuring out, making a guess, which one of these two is going to have a higher boiling point, most likely. All right, so the two molecules we're going to compare are ammonia, NH3 is ammonia, and methane, CH4. Now, as we've been talking about, the kind of intermolecular force really depends on whether you're polar or nonpolar. So we're going to go through step by step. We're going to figure out, is the molecule polar or nonpolar? And then once we know that, we'll be able to figure out the kind of intermolecular force. Polar guys do dipole-dipole, nonpolar guys do dispersion, and so on. So how do you figure out if a molecule is polar? Well, you got to draw out the Lewis structure. In the interest of time, let me just put them up. This is the Lewis structure for ammonia. You've actually done it before in some previous videos. All right, and methane, this is its Lewis structure. Now, once we know that, the next thing we can figure out is, are you polar or nonpolar? So how do you do that? Well, the way you figure out if you're polar or nonpolar is you got to look for, you look up the electronegativities, right? And let's see, let's put them up here. Carbon is 2.5, hydrogen's 2.1. I could do it over and over and over, but all the bonds in this molecule are between carbon and hydrogen. They are, if you subtract 2.5 minus 0.1, all the bonds are nonpolar, right? All the bonds are nonpolar. You need a difference of 1/2 to be polar. So if you have nonpolar bonds and all you have is nonpolar bonds, you have to be nonpolar overall. You have to be a nonpolar molecule, right? Because polar molecules contain polar bonds. So in methane, we have nonpolar bonds. So if you only have nonpolar bonds, you're going to be nonpolar overall. To be polar, you have to have polar bonds and more stuff, the lone pair or the different atoms. All right, let's look at ammonia. All right, for ammonia, I'm going to do the same thing. I'm going to figure out whether he's polar or nonpolar. So how do you do that? You look up the electronegativities, and again, all the bonds are identical. They're all bonds between nitrogen and hydrogen. So if I look up the electronegativities, we have 3 and 2.1. So if I subtract those, that difference is 0.9. Those bonds are polar. And not only do we have polar bonds, what else do you know notice that's important? Oh, a lone pair on the middle atom. Those lone pairs on the middle atom, polar bond and a lone pair on the middle atom, ammonia is polar overall. All right, polar overall. All right, so now that you know if you're polar or nonpolar, you know the kind of intermolecular force. If you are nonpolar, the only thing you got holding you to your neighbor are those weak, wimpy little dispersion forces. All right. If you are polar, you're going to have dispersion forces. That's true. Everybody's got dispersion forces, but you actually have something even better. Now, be careful. Let's look at this one. Oh, I think we talked about this in the last video last time, didn't we? If you have NH as part of your structure, you can hydrogen bond. And hydrogen bond, wow, that's really good. That's the strongest kind of intermolecular force. So you have dispersion forces. Everybody's got dispersion forces, actually. But you have something even better, hydrogen bonds. And hydrogen bonds are really strong. So if this thing has got strong intermolecular forces, and this guy only has weak intermolecular forces, oh, why don't you make a guess? Which one is going to boil at a higher temperature? It's going to be ammonia. If you have strong intermolecular forces, you're going to be harder to separate from your neighbors, and that's what boiling is. When a liquid turns into a gas, it's really just separating from its neighbors. So if you have strong intermolecular forces, I'm going to guess ammonia is going to boil at a higher temperature because it's got hydrogen bonding. All right, well, obviously, well, maybe not obviously, but we can look it up to make sure. And if you look it up, ammonia boils at -33, and the methane boils at -258. So notice they're both negative. So this is actually a higher temperature. -33 is higher than -200. Okay, so yeah, our prediction actually is right. Ammonia should boil at a higher temperature. All right, with that, let's do one more. Let's do one more. Can we figure out the kind of intermolecular forces and use that to guess properties of a molecule? All right, let's do one more. All right, so on our second example here, let's look, we're going to compare two molecules again, and this time I want to be able to guess, I want to predict which one is most volatile. So what does that word mean again? Oh, we talked about it in a previous lecture. Volatile means which one is the, we'll say, easiest to turn into a gas. Which one is the easiest to turn into a gas? So that's going to be the fella with the weakest intermolecular forces. The fellow with the weakest intermolecular forces is going to turn into a gas the most quickly because they're not stuck to each other. Now, as far as that goes, that means, well, we're going to have to figure out the kind of intermolecular force. And before we can do that, we got to know whether you're polar or nonpolar and all that. So this time we're going to compare two molecules that are a little bit bigger, just because I want to show you some that are maybe just a little trickier. So let's compare methanol. Methanol is actually like wood alcohol. Like you'll find it down at like Home Depot and stuff as a cleaner, a solvent. All right, so let me draw it up. This is the drawing of methanol. And then let's compare it to the kind of alcohol you drink. And if you drink beer and wine and that kind of stuff, you're drinking ethanol. Now let me draw up ethanol. This is what ethanol looks like. Now, you'll notice both of these guys are maybe a little bit bigger, a little more complicated than what you're used to seeing, but that's okay. We can still figure it out. So first thing I'm going to do is figure out whether they're polar or non-polar. Now, to do that, really, what do? You got to look for a polar bond, and you got to look for different atoms attached to the middle atom. So you notice sort of there's not really just one middle atom. So we could look at any middle atom and figure that out, or any atom to any one of the atoms in the middle here. So let me kind of show you what I mean by that. All right, we'll see if this makes sense to you. I hope it does. So for example, when I look at oxygen, and well, let's look up the electronegativities. It's 3.5 and 2.1 and 2.5. If I look at what's going around oxygen, it's got polar bonds around it. Actually, both bonds are polar, right? It's got a polar bond with hydrogen. If you subtract, you get more than a half, and it's got a polar bond with carbon. So it's got polar bonds. And on that atom where we have polar bonds, you actually also have a lone pair. And gosh, you even have different atoms attached. So if you put that all together, that's going to make it polar. Polar bonds in this thing, along with different atoms around that around the oxygen, and even lone pairs on the oxygen. All right, so yeah, it's a little bit more complicated. So maybe it's not quite so straightforward, but you're kind of looking for the same stuff, even in a bigger molecule. Now, let me also do that over here, right? So you're going to have same thing going on in ethanol, right? We've got our polar bonds between oxygen and hydrogen. It's really the same thing. And yeah, we got a polar bond, and there's lone pairs on the oxygen. Yeah, ethanol is also polar. All right. Now, wait a minute. There's something else I'm wondering, did you notice something else special about these guys as far as kind of intermolecular forces? A special group of atoms, that gives you a really strong kind of intermolecular force. Oh yeah, both of these guys have OH as part of their structure. If you've got OH as part of your structure, you can hydrogen bond with your neighbor. So the fact that it's polar, I wanted to explain that to you. It's not really super critical to come up with the answer. If you see OH, or NH or FH, you can hydrogen bond. You don't even really need to worry about is it polar or not. It will be. All right. So yeah, we talked about that just to make sure you heard about that too. All right. So, well, if I want to decide which of these guys is going to be the most volatile, let's see where we're at right now. Both of them can hydrogen bond. So wait a minute. If they both can hydrogen bond, how is one going to be different than the other one, right? In the last example, one of them did dispersion, and then which was weak, and then the other guy did, what was it, dipole, which was stronger, so you could kind of tell them apart. Well, right now, both of them seem to be kind of the same. Both methanol and ethanol can hydrogen bond. So I kind of feel like there's a tie here for intermolecular forces. And it is true, but wait a minute. What else is going on besides hydrogen bonding? What else goes on between all molecules? All molecules also have dispersion forces. So, okay, well, dispersion forces. Well, if they both have dispersion forces, I'm going to have to write it here. If they both have dispersion forces, I feel like they're still tied as far as the way they're going to behave. But wait a minute. Do you remember what I talked about? Dispersion forces get stronger as the molecule gets bigger. So they have, I don't know, how should we say that? Ethanol has better dispersion forces because it's a bigger molecule. You know, it's got more carbons and more hydrogens. If we added up the weight off the periodic table, we'd get a bigger number. It's got better dispersion forces than methanol. Methanol would have, I guess we'll say, worse dispersion forces because it's tinier. Those dispersion forces, they get better as the molecule gets bigger. They never get super great, but they will get stronger as the molecule gets bigger. All right, so with that little bit of information, all right, let's see if you can predict this one again. Which one is going to turn into a gas the easiest? Okay, it's going to be the guy who has the weakest forces comparing these two. And the fellow who has the weakest forces, that's the methanol. The methanol has dispersion forces which are not as powerful as ethanol. All right, so I hope that made sense. All right, so with that, let's see. I think that's all we're going to do in this video. Is that the end of this one? Let me check. Oh, I was going to show you one more just to kind of compare. Again, you kind of see these aren't the molecules on another page, but again, if you have different kind of intermolecular forces, you get different properties. And so, for example, let me show you one more thing here. We're comparing methanol to ethanol. This guy would have hydrogen bonding. And I don't think I'll take the time to go through all this again. But this guy would be nonpolar. It only has dispersion. So if we figure out you have worse intermolecular forces, you're going to have different properties than somebody with better intermolecular forces. Guys with worse intermolecular forces, weaker, you're going to have a lower boiling point, and you're actually going to also have a lower melting point. All right, so yeah, determining the kind of intermolecular force, that's going to help us understand the properties of molecules. So with that, that's it for this part. There's going to be another part that's a little bit different, a little bit not quite on the same topic, but it does have to do with solids, liquids, and gases. So that'll be part B coming up in just a minute. That's the end of part A. Hopefully this is making sense. If not, let me know, and I can be glad to answer some questions.